In this video, we'll be putting together our previous knowledge of graphing polynomial and rational functions to answer something called an inequality. Let's get started. We begin by looking at a graph, and maybe you can figure out just by looking at it, of a rational function. That's right. It's rational again because we have a break in the graph, namely a vertical asymptote at x equals -1. So I make a little note of that here. We have a nice vertical asymptote at x equals -1. So that's where we have our break in the graph. The graph then breaks into two pieces. Now the question that they're asking me is, when is this function, f of x, less than or equal to 0? So that's called an inequality. Now most students get stuck right there. They don't understand what in the world the question is asking. So let's see if we can break it down a little bit better. In English, what this is trying to ask you is, for what inputs or what x values would your outputs, your y function values, be negative? That's all it's saying, be negative or 0. Negative because it's saying less than 0, and equal to 0 would be equal to 0. So our job is to first look carefully at the graph and find those places in the graph where the y outputs, the y values, are below the x-axis or even equal to the x-axis based on that or equal to. So let's take a look. Let me grab another color and see if we can find this. How about brown? There we go. So it looks like, from my perspective, that to the left of this asymptote, to the left of x equals -1, the graph is always above the x-axis, isn't it? In fact, it's even above a horizontal asymptote y equals 1. So we do have a horizontal asymptote y equals 1 in this picture. Okay, so it looks like this part of the graph is always above the x-axis, which means our y values are not less than or equal to 0 there. When are our y values less than or equal to 0? Well, clearly, I hope you see that to the right of the asymptote, this part of the graph, I'm trying to write on top of it, sorry, is definitely below the x-axis. Those are negative y values. So y values to the right of -1, so I could write that in my solution set as parentheses -1, so to the right of -1, until I get to the x-intercept. Now at -2 itself, the x-intercept here, at +2, at +2 itself, our x-intercept, which is 2, we notice that the graph is supposed to be equal to or less than. So we could include that point, which would mean at +2, our x-intercept, we would use a bracket. So our solution set, the possible x values or inputs that would give us outputs which are less than or equal to 0 would be any x value between -1 and 2, including 2, but not including -1. And again, the reason -1 must be excluded with the parenthesis instead of the bracket would be because it's a vertical asymptote. It means an input which would create a problem for our output. Okay, so today what we're going to be doing is doing just that. We're going to be looking at graphs and answering the question, when is this graph below the x-axis or above the x-axis? A very basic concept, but knowing what they're asking is the key. Let's get started with some other examples where it's not quite as obvious. So in the example that we're going to be looking at next, it says x squared minus 8x is greater than or equal to 7. And we're asked to solve that inequality. Now, if this was an inequality like x minus 8 is greater than 7, you would know how to do that. That's called a linear inequality, where you would isolate x on one side and you'd get your answer right away. But when we have a quadratic or a degree 2 inequality, also known as a polynomial inequality, or even a rational function, a fraction with an inequality sign, we can't just get x by itself. Instead, if we're going to do it from a graphical perspective, which is what I would recommend if you're going on in math, is to make sure that you know how to graph these and analyze their graphs. What you want to do first is really get 0 on one side. But the side that will make most sense to students typically is on the right side. So we're going to work to get 0 on the right side. So that's like step 1, if you will. So looking at our example here, x squared minus 8x is greater than or equal to -7. To get 0 on the right side would mean, that's right, that -7 must move to the other side of the equation, meaning I have to add 7 to both sides to maintain balance. So this would become x squared minus 8x plus 7 is greater than or equal to 0. Okay, with that in mind, now what we need to do is step 2. In step 2, what we are after is to graph the function that we have on the left. So here is our function on the left. We would like to graph the function on the left using intercepts and any asymptotes. Now this will only happen if we have a rational function, right? If we have a polynomial like we do here, there are no asymptotes because it's continuous, right? There are no breaks in the graph. So we're going to simply use intercepts. Now, in our previous lessons, we've discussed how to find all x-intercepts for a polynomial function, also known as the real zeros of a function. That might ring a bell. So feel free to go back to other videos if you are getting stuck on how to do that, okay? But in this case, this is such a nice, small trinomial degree 2 quadratic that we should be able to factor this immediately. So what factors of 7 with the same sign add up to negative 8? That's right, negative 1 and negative 7. So x minus 1 and x minus 7 should be my factors there. You can verify that, of course, by FOILing or multiplying it out. And what we have now, if this is our function, we're going to be graphing that function and then answering the question, when is it greater than or equal to 0? So let's see how we would graph that, knowing what we know about polynomials. If we have an x-intercept of 1 and 7, let's put those on our graph. So at 1, we have an x-intercept, 2, 3, 4, 5, 6, 7. There's another x-intercept, so that's at 1 and that's at 7. With that in mind, and because we know the degree was a degree 2 polynomial, which is even, remember what that meant for end behavior? If you have an even degree polynomial, that's right, they're going in the same directions, either both up or both down. Then we would look at the sign of the leading coefficient, which in this case is positive 1. So it's positive, that must mean that they're both going up. So I could immediately start the picture looking something like that, right? We know that we are going up as we go left and right forever. Also, we could even find the y-intercepts if we were so inclined, but what was really essential was the x-intercepts. The y-intercepts are just nice if I want a nice picture. For the y-intercept, I would let x equal 0, and in this case, if you let x equal 0 here and here, you just get 7. So 1, 2, 3, 4, 5, 6, and 7. So if you were curious about how pretty this looks, it actually goes through 7 here, so I'd have to continue up along this way until I cross at 7. Similarly, if I went the same direction, let's say we went over 1. So if I went over 1, I'd have to go up to 7 here, and this graph would look something like that, going up and ending 7. Okay, so we have what looks like a parabola with nice symmetry along the axis of symmetry. So we'd have a vertex somewhere, and remember from your earlier classes, you know how to find the vertex using either completing the square or the vertex formula, getting your h value with negative b over 2a, plugging it in to find k. So you're welcome to do that. It will be somewhere down here. So feel free to find your vertex on your own, okay? Feel free to do that, hk. Okay, but as far as what we are interested in right now, we were interested in knowing that this graph definitely crossed, and we knew that because the multiplicities of each factor were 1, they're odd, so we crossed. And now we can answer the question. So step 3 in this process of solving an inequality graphically, after you get 0 on one side and graph what's on the left, we would then ask ourselves, when is my graph above, below, or on the x-axis, according to the sign of the inequality? Our sign is greater than or equal to. So this is asking us, when is my graph above, because of greater than, or on, because of the or equal to, the x-axis? So once we know that's what it's asking, we should be able to answer that pretty nicely. When is it above? Well, to the left of 1, it's above, right? To the left of 1, it's above. When is it on? Well, at 1. So I could say from negative infinity until positive 1 with a bracket, meaning I'm allowed to actually equal 1 because my y value, my output, would be 0 at that location. When else? Well, starting at 7, so union or 7, including the 7 because it's equal there. Going up to forever means I'm going to the right forever as well. So those would be the potential x values which would make this inequality true. Now, if you really wanted to check yourself, what could you do? Yeah, that's right. you could pick any number in these intervals and plug them in for x in your original inequality and verify that, in fact, the left side is greater than or equal to -7. Okay? So to solve this inequality graphically, just to summarize, we got 0 on the right by moving over this -7. We graphed the function on the left using intercepts this time. We could find the intercepts using any of the methods we previously discussed, but in this case, factoring was pretty nice. And then finally, we determined when the graph was on or above the x-axis because our graph was supposed to be greater than or equal to 0. Now, I do want you to be aware that if you were to ask someone to help you who may have done this a different way, the way that they might have done it is called the analytic approach. So while I don't spend a lot of time on it, I do want you to at least see what it is in case someone talks about it, or if you look in the book and they show you another way. The analytic approach would say, on a number line, put down any intercepts or asymptotes. So we found our x-intercepts were 1 and 7. And then what you would do is you would pick a number in each region to the left and to the right of each number, each intercept or asymptote, x-intercept or asymptote, and you would see whether or not your graph is positive or negative there. So for example, if I picked something in the region, let's pick white here, the region to the left of 1, how about 0? If you put in 0 into your function, which is right here, right? If you put in 0 there, you're getting 0 plus minus 0 plus 7. So you're getting a positive answer, right? So you're getting a positive region, which is true. That's a positive region, isn't it? The region to the left of 1 was positive. What about between 1 and 7? Well, how about 2? If you put f of 2 in here, that would mean 2 gets plugged in, either to the factored form or to the expanded form. Now, in the factored form, it's quite easy because 2 minus 1 is 1, and 2 minus 7 is -5. So if I have 1 times -5, I have a -5. In other words, I have a negative in that region, which is what we see in our graph. We have negatives between 1 and 7. And finally, the last step for the analytic approach would be to pick a number to the right of 7. How about 8? Again, if you plugged in 8 into the factored form, 8 minus 1 is +7, and 8 minus 7 is +1. So we get a positive result, which is exactly what we expected to the right of the value x equals 7. So this is another way that you might sometimes see in a textbook or a tutor going over how to solve inequalities. I just wanted you to see it at least one time. You're welcome to use either approach, but I will tell you that if you plan to go on in math, you really need to be an expert at sketching the graphs by hand and then analyzing them. So make sure you really stretch yourself as you're doing your practice. Okay, let's practice some more putting this into use. Here we go. Example 2. Here we're given the inequality x cubed is less than -8. And we're told to write our solution in interval notation. So I begin by noticing this is not a good old linear inequality where I can just get x by itself. This is a polynomial inequality, meaning I need to first get 0 on one side. So that was our first step, meaning this would be x cubed plus 8 is less than 0. Now my job was to graph whatever was on the left. So my function here, if you will, my function is the polynomial x cubed plus 8. I want to graph it. To graph that, I could do a couple of things. I need to graph it with the intercepts for sure. I need the x-intercepts. So I could just jump right into finding my intercepts. That is totally fair game and probably the fastest way to go, to be honest. So if you were to get the x-intercepts directly, remember what that means. To be on the x-axis, your y values must equal 0. So if you let your entire function's output, your y value equals 0, 0 would equal x cubed plus 8, which would mean that -8 would equal x cubed. And how do you solve a degree 3 equation like that? Well, in this case, if it's something cubed equals a number, you could take the cube root, the third root. And it's possible to take the third root of a negative. It's just not possible to take the square root of a negative, right? So let's see, this would mean that x equals what number? That's right, -2, because -2 times itself 3 times would give me -8. -8 was a perfect cube, if you will. Okay, so what we now know is that the one and only x-intercept is -2. So I'm going to put that on my graph. That's the one x-intercept, okay? And because this is a polynomial, we know that there are no asymptotes, there are no breaks in the graph because there are no denominators that could be problematic. So it's going to be continuous left and right forever. We could then look at our degree. Degree 3 is odd, meaning that at the ends, as I go to the left and the right forever, are we going in the same direction or opposite directions? That's right, we're going in the opposite directions, either increasing or decreasing from left to right. And to determine whether we're increasing or decreasing, we looked at the sign of the leading coefficient. And the leading coefficient is a +1, meaning we are increasing from left to right. We're also noticing that at the actual intercept, here, we are going to have a degree of 3, so it's odd, so we're going to cross through. So we're looking something like this, crossing through. Now, if you remember, this is the snake graph. We've actually remembered this was the snake that's been shifted up 8 units, if you remember it that way. You could have also gotten that by looking for the y-intercept, and you could have found the y-intercept by letting x equal 0, which is f of 0 in this situation. But 0 cubed is 8. Sorry, 0, and 0 plus 8 is 8. So if you have 0 plus 8, we do get 8 here, because 0 cubed is 0. So we do get our y-intercept of 8. So let's take a look at what that would be. 1, 2, 3, 4, 5, 6, 7, 8. That's my y-intercept. So this was actually the original snake function shifted up 8 units, and we've studied that in previous courses. So this looks more like this. It's shifted and then it's turning at that location. So something like that's happening. All that we really care about, though, for our purposes, as ugly as my snake is at the moment, all we really care about is our third part of the question, right? The third part of the question is, when is my graph, in this situation it was, where is it here? Less than 0. When is my graph less than 0? So in this case, we're really saying, when is my graph below the x-axis? So let's see if we can answer that question. When is my graph below the x-axis? Well, it looks like because it's a snake, it's going to go down forever as it goes left forever, meaning that there's no opportunity for it to turn back around and go back up and over the x-axis again. In fact, the only x-intercept was -2. So in this situation, the answer would be, see if you can write it out yourself, you can feel free to pause it. The answer would be any value to the left of -2. Any value to the left of -2 would give me an output of negative values, less than 0. So I would say -infinity until -2 with parentheses. Again, why not brackets? That's right, because we don't have an or equal to here. You're not actually allowed to equal an output of 0. You must be below 0. That's why -2 itself is excluded. Only values left of -2 would produce this. And again, you should check to make sure this makes sense, right? Pick a value in that region, like -3, for example. If you picked a -3 and you plugged it into the original, right here, would this be true? Well, -3 to the third power would be -27. Is that less than -8? Yeah, so that input did create the right output. All right, so we've done one together now, actually 2 really, where we've had polynomial inequalities. We got 0 on the right side, we graphed using our intercepts and our end behavior, and then we answered the question, when is my graph on, above, or below the x-axis? What's next might cause your head to spin a little bit. Rational inequalities. So you first need to be an expert at rational functions. So I'm going to tell you now, if you're not, that's okay. Know yourself, right? Go back, pause this video, and watch our video on graphing rational functions so you feel like you're a pro at the rational functions, and then you'll be able to answer the next question. Okay, but for those of you who are ready, let's get to it. Solve the inequality using interval notation. And the inequality we have here is 2x plus 6 over 2x plus 1. And it's completely supposed to be greater than or equal to 3. Its output must always be greater than or equal to 3. Okay, and by the way, we're doing everything in a very abstract context, which I know can be very problematic and painful for students who don't like thinking abstractly. But there are a lot of applications where this makes sense. What we're really saying is, if you need your output, this could be amount of money, this could be anything, to be greater than or equal to 3, what inputs would you have to have? That's really what we're talking about. And we use that type of language on a daily basis. If I need to make this much money per year, how many hours do I need to work a week? Same type of thing. If I want to make an A in this class, what do I need to get on test 5? Same type of thing. We use inequalities all over the place. We're just happening to be doing very abstract versions of them right now. Okay. So let's continue along. We would start with our first step, right? We would want to get 0 on the right side. So that would be 2x plus 6 over 2x plus 1. But to get 0 on the right side would mean that 3 gets subtracted from both sides. So we take minus 3 on both sides, and now we have greater than or equal to 0, because 3 minus 3 is 0. Okay, now this is the step where students, they don't really struggle with this material, they struggle with previous material. And by that I mean they struggle with adding and subtracting fractions. There are many, many videos out there about adding and subtracting fractions. If you ever want to know about how to find those resources, you can always contact me. But I do think that is something you would need to practice, right? So if you have 1/2 minus 3/2, or 1/2 minus 3/4 rather, how would you combine them? That's right, you would get a common denominator. And similarly here, this is a skill that you really need to become an expert on if you're going to move on in math, okay? Right now, if you have -3, you really have a -3 over a 1, which would mean that if you wanted a common denominator, you would take everything from the first denominator and then anything new, any new factors in your next denominator. So your least common denominator would really be 2x plus 1, wouldn't it? So I'll just write it out slowly for you in case you are struggling with this. But if you can go faster, more power to you. That's great. So what I'm going to do is I'm going to multiply my second fraction by what it's missing in its denominator on top and on bottom. This is a mistake students often make. They put it on the bottom without putting it on the top, and that's illegal. You have to balance it out. Otherwise, you just inserted something into one side of the equation that's not on the other. So you have to have it on top and bottom because that's really like multiplying by a 1, which doesn't change the net result of anything. You're making them both bigger at the same time. So we're going to multiply the top by 2x plus 1 and the bottom by 2x plus 1. Now the shortcut of this is just to write one fraction line and put 2x plus 1 on the bottom and then multiply -3 by what its denominator is missing. And that's what many of you probably started doing. Feel free. I'm just going very slowly for those who need it, okay? So this becomes 2x plus 1 as our least common denominator. And our original numerator for the left term was just 2x plus 6, so I'm copying that. But on the right term, I have to be really careful. When I grade 100 tests, I usually see about 50 students make this mistake. So you ready for it? They start distributing, but they forget to distribute the second sign, okay? And that ruins everything. So make sure you watch out. You have to distribute. Make a little note to yourself if you think you might make that mistake, because if we start practicing the error, we're going to keep doing the error, right? We want to catch our errors early. So let's see what we get. -3 times 2, that's -6. -3 times 1 is -3. I forgot my x though, that's important. So I have -6x, and then I have a -3. So this is again the sign that most students miss. Okay. Once you have that, you can combine your like terms. This is all basic algebra right now. We haven't even gotten to the fun new stuff, but we're just trying to get it into a place where we can recognize what's going on. So let's take a look at what this is. 2x and -6x are like terms, so our leading term is now -4x in our numerator. We also had a +6 and a -3, so our constant term, when we combine 6 minus 3, is +3, isn't it? Over the denominator, 2x plus 1. Now we just went through all of this work to get to step 2. In step 2, we're finally going to graph this function, okay? This is like our f of x. And eventually we want to know, when is this function greater than or equal to 0? That's ultimately the question. Okay, so now that we finally have a grasp on what we're dealing with, we have one single rational function that we've worked really hard to get put together correctly. Now we're going to graph it and see when we are above or below, in this case above, right? Above or on the x-axis. So what do we need to graph a rational function? Well, as you noted in the previous slide, when we went over the steps, we mentioned that you need intercepts, x-intercepts, and any asymptotes. So let's talk about how we could do that, okay? So for this one, if we were looking for x-intercepts, for example, we would let y equal 0, but that would mean the entire fraction ends up equaling 0. So what would that mean here? If this entire fraction equals 0, the numerator would have to equal 0. So that would mean that -4x plus 3 would equal 0. In other words, solving that linear equation for x, getting x by itself, you would move the 4x perhaps to the other side and eventually get that x equals 3 over 4. And once you get x equaling 3 over 4, you could put that on your graph. That is an x-intercept. So let me get another color here. 3/4. So if this is like 1, 3/4 might be around there. So I put my x-intercept on the graph. Okay, now that I have my x-intercept on the graph, I would also need to find my vertical asymptotes, or holes. Okay, so for my vertical asymptotes, or holes, that's when we look and we see, do we have any issues in our denominator? Do we have any breaks in the graph? So in this case, nothing cancels, so we could just set the denominator equal to 0. 2x plus 1 equaling 0 would mean that 2x equals -1, so x would equal, that's right, -1/2. So this would be my vertical asymptote, and I could show that on my graph at -1/2. So if this is like -1, -1/2 might be here. At x equals -1/2. Okay, now there was one other piece to get a decent sketch of a rational function, and that was a horizontal or a slant asymptote. Again, if this is not familiar to you, if you're not a pro, feel free to go back to our previous video on graphing rational functions. So to do the horizontal asymptote, we would say we need to compare our degrees of our numerator, which is 1, and our denominator, which is also 1. Since they're the same, we do have a horizontal asymptote, and it was the ratio, so the fraction, of the leading coefficients, -4 on top and 2 on the bottom. In other words, if you were to erase that, that's just simplified to -2, that's right. So our horizontal asymptote is at y equals -2. Put that on my graph. So -2 would be down here somewhere. So we have our horizontal asymptote graphed, and that actually, once again, gives us enough information to draw a sketch. All we care about, if you go back to big picture here, big picture, because we're getting stuck in the details, step 3, what we're really looking for is, when is this graph going to give me an output greater than or equal to 0? In other words, when are my y values, my outputs, on or above the x-axis? So that is my question that I'm looking to answer. Okay, so to do that, we need to get our sketch. We're almost there. We are super duper close. So let's get a color here. How about, what haven't I used here? Let's do brown. Okay, so since we know our x-intercept was at 3/4, we could have also found a y-intercept if you were so inclined. By letting x equal 0, that would make this term go away. That would make this term go away, and you would just have 3/1, or 3. The reason I say it might help to get that is because you have a better sketch. 1, 2, 3, there's my y-intercept. Now what I don't want you to do is to think that's going to be part of our solution, because it's not. The only potential parts of our solution for an inequality like this are going to have as our bounds either an asymptote, a vertical asymptote, or an x-intercept or a hole. Those are going to be what we're talking about. So only x values will determine when this is happening, okay? But the y-intercept was helpful in drawing the picture. So now I can see what's happening in this quadrant, or in this region rather. We should be approaching the asymptote from the right and approaching this asymptote as we go to the right forever. So this part of the graph looks like that. On the other side, you could use test points if you want to get a safe pair of points that you can know exactly where you are. But you really don't even need to, technically, because to the left of this vertical asymptote, we don't have any more x-intercepts allowed. The only x-intercept was at 3/4, which was to the right of that asymptote, meaning that to the left of the asymptote, I can't cross that x-axis ever again. So my graph must look something like this. It must be below, in other words, below that horizontal asymptote, since there are no more x-intercepts allowed. The only x-intercept was at 3/4. So once I have a basic sketch, and the only thing I really absolutely needed were the x-intercepts and the vertical asymptotes. Those were the two things I desperately need in order to answer the inequality. For the sketch, y-intercepts are good, horizontal asymptotes are good, but that's all I absolutely needed. Now I can definitely answer this question, I hope. So take a moment if you want to pause the video and see if you can answer the question. What are we asking again? When is this graph, because it's greater than or equal to 0, on or above the x-axis? See if you can find the parts of the graph which are on or above the x-axis, and write them out. Okay, I notice that the part on the left is definitely below the x-axis, so that's disqualified. But the part between the asymptote -½ and the x-intercept 3/4 is above the x-axis. So between the asymptote, which I can never reach, so I'd use a parentheses, so between the asymptote -½ and the x-intercept 3/4, which I am allowed to reach because it says or equal to, and it definitely exists there, so I can use a bracket, my graph is going to be on, because of the x-intercept, or above, between them, the x-axis. After that, you'll notice that you're always below the x-axis. Now, there could be cases where, especially in a rational function, parts are going to be above in different locations, so you'll use your union symbol to get those other locations. But for this one, that's the only time this happens. Now, once again, I really encourage you, as you're doing your practice, in addition to doing it graphically, try the analytic approach. Draw out that number line, put your asymptotes and your x-intercepts on it, pick test points, and see if you're positive or negative in each region. If you can do things in more than one way, then you're going to be in much better shape understanding what's going on in the future and checking your answers on tests. All right, it's all up to you now to practice. Remember, math is not a spectator sport. I'll see you next time.